Everyone, I hope you are in good shape. So let's start with something very important in this video today. We are going to discuss about async await, but we are going to differentiate the workings of async and await in Node.js and Rust. So both Node.js and Rust lets you write async await. The syntax almost kind of looks identical, but they kind of trying to solve a same problem, that is concurrency, but in a different way. Node.js uses a single thread and it uses a smart queue system or a event loop system to solve that particular problem, while Rust uses a thread pool and something called futures. And by the end of this video you will have a complete understanding, and you will have the understanding of why it really matters when you have to choose between Rust and Node.js. So let's get into it. So before we go any deeper, let's understand something called IO. So you must have heard IO, right? So IO means input output. It means anything that your program has to wait outside of the CPU and wait for the response, and at that time your CPU has to sit idle. So that is called an IO. It could be anything. It could be a network request. It could be reading a file, writing to a file, or it could be reading from a user's input or writing to the terminal. So the key thing is, during an IO operation, our CPU kind of sits idle, and it kind of sends the request, then wait for the response, then do the further processing. All right. And the opposite of IO are the CPU bound works. CPU bound works like image resizing, video editing, running an ML inference. Here our CPU comes into the picture and does the most of the heavy lifting. He doesn't have to really wait for all the things, and he just have to start work from the start to the end. The CPU kind of lies very flat there. So why I am discussing this thing over here? Because these are the distinctions that really help you to choose between Node.js and Rust. So if you are really working on to something that does the CPU heavy lifting, then you have to choose maybe Rust. And if you are really working on the IO operations kind of thing, then Node.js perform well as well. So let's start with Node.js and let's understand what a call stack is. Alright, so let me just pull the visuals for you. So as you can see over here, Node.js runs our JavaScript on a single OS thread. And when the code runs, it goes into a call stack. As you can see, I have like kind of defined a call stack over here. Currently it's empty. So it's a part of a V8 engine that execute our code line by line. All right. So console.log is the simplest example here. So it goes directly into the call stack, runs immediately and prints, and then the stack kind of moves on. It never touches any queue. It never waits, because it's purely synchronous. So let me just show you. So it's a console.log tab, and when I run demo, as you can see, when I run demo, it directly goes into the call stack and it directly executes. So as you can see on the output, so this sync, that because it's a synchronous operation, it runs directly on the call stack. It doesn't wait for anything and doesn't go on the queue. So as you can see, there are no queues involved over here, because console.log never waits. The program, the JavaScript engine that we have, it runs the synchronous thing directly, putting into the call stack and just directly running them. All right. Now let's switch to the web API and libuv. So when I just go on over here on the web APIs, so when we call something asynchronous, so over here, as you can see, when I call something asynchronous like set timeout, fetch, or file system.read file, asynchronous read file, the JavaScript doesn't actually do that work itself. So because these are not the part of a JavaScript, they are the part of a browser's API called web API. So JavaScript really doesn't actually do that work itself. It hands the job off to the browser's web API, or in the Node.js case to libuv. It's a C library underneath Node. So as you can see, these are the steps that you can see on your screen. Step 1 is call stack. So it's my JS code. So everything runs on a call stack in JavaScript, and whenever it encounters something that is not JavaScript related, it gives it to the web API or libuv. So all the async work is done over here, like timer. So timer is not the part of JavaScript. So do all the network calls. They are handled by web API, and when web API is handle that task, they just did the task on a separate thing, so that the main thread on the JavaScript that runs, it can execute the next line of code. Right. So it doesn't have to really set its head on these things. These are handled by a web APIs. So let's say in our case, we have a timer over here. So the timer queue over here is quite very specific, but it should not be there. It should be a task queue, because the timer queue I'm relating over here because I'm just passing a timer over here, so it's a timer queue. If it's any API request, let's say I'm calling any web server, then it will go into the microtask queue, and the event loops keeps on checking that all the queues, and we have a priority over there as well. So let's say there is a timer queue, there is a microtask queue. What event loop will do is it will give the priority to the microtask queue very first. That we'll see on our in the upcoming tab over here, as you can see. So let me run the demo here. When I run demo over here, let me just pull it up. So when I run demo over here, as you can see, the set timeout goes over here. It moves to the web API, and once the web API finishes, it pushes this thing into a timer queue, and the event loop then picks it from the timer queue and put it on the call stack. And that's how the executing works over here, right? So as you can see on the output log, a set timeout code, and the callback named to the web APIs. It's a synchronous thing because the console log is written over it, right? But before that, because the timer is there, so it handed it over to the web APIs. Web API immediately called that thing, and the main thread is free over here. Once this timer is finished, it gets pushed onto the timer queue or task queue, and later on event loop picked it from the task queue and put it on the call stack to just perform the console log, right? So this is how this thing works. The same for the fetch IO. This was the timer example. Let's understand if there is a network core involved. So let's say I call a fetch, then it will pass it to the libuv OS or web APIs specifically, and it will do the work. The main thread is freed over here, and when the IO finishes, the request get pushed onto the microtask queue, and the event loop keeps on listening onto these queues, on the IO queue, on the microtask queue, or in the task queue. So based on the priority order, it pass it on to the call stack. So let me just run the demo over here. As you can see, the fetch goes to libuv, and once the task is complete, it goes onto the IO queue and then microtask queue, and then microtask queue is given a priority, so it gets pushed into the call stack. So let's understand what all are the priorities over here when it comes to multiple operations. So let's say we have an IO callback, a timer, a microtask, all of these things, right? It's like a JavaScript program, right? So we have some asynchronous things, some synchronous things, some timers, some API events, like we have to fetch from the outside world in our case. So let's do that. Let's say our program involves some of the timer, some IO, some microtask, again some oh my god, my mouse. Okay. IO, timer, microtask, then microtask, timer, IO. So these are the queues. So it doesn't matter right now. But the thing is, when I run the loop, so event loop is how it checks based on the priorities. So as you can see, the microtask queue will given the priority at the very top. Okay. So if I run the loop, as you can see, microtask queue is executing right now, again, then the timer, then the IO callback. As you can see, this is done like this. So it's a priority given between the each queue. Now here you can kind of exhaust Node.js. Why? So because imagine there is a API request or a microtask queue item. That means an API request that creates a promise, let's say. And when that promise resolve, it goes into the microtask queue. So let's say there is a promise that again creates a promise that again creates a promise, and so on. So you see all these things on the other queues, like the task queue or the callback, IO callback queues, they really don't get a chance. Why? Because microtask queue has been given priority, right? So if you really want to check out how event loop works, you can check out the video of Akshay Saini on YouTube. That's quite fantastic over there. So that will really help you a lot understanding this thing. All right. So this is of Node.js, right? How Node.js kind of works in terms of async await. When you call this thing, any async await or any fetch or any API call, it's not about writing just async and then await, because in Node.js we just forget, right? We write async await and rest thing is done. So this is how the back on the under the hood it works. It just handed the request to the web APIs, and the main thread is freed at that time. All right. And web API do its work, put it into the microtask queue, and the event loops keep on checking on the multiple queues to just push those into the call stack based on the priority. Amazing. So this is how the async await of Node.js works. Now let's go into the Rust, how Rust is different in that case. So on the Rust, as you can see, if I go on the thread pool, so when you use async await on Rust, you have to use a runtime, and the most famous one is Tokio, right? So when you use Tokio runtime, what Tokio does is, as soon as you start your program, you have to define a macro, that is Tokio main macro, that mostly do the heavy lifting of creating a thread pool, and at the very start it creates a thread pool based on the cores of your CPU, right? So if you have a 4-core CPU, then it will create 4 threads, or maybe worker threads you can say, into a thread pool. So it works based on the thread pools. So unlike Node.js where we have a single thread, but on the Rust we have an entire thread pool. So tasks are basically divided into these worker threads or these threads, right? So let me just give you an example over here. So I have the cores over here. Let's say I want to increase it to the 4. So there are 4 worker threads that are sitting idle right now. Let's say I want to spawn a task. So let's say I spawn multiple tasks over here. So you can see when I spawn multiple tasks over here, as you can see, Node.js assign into a single a row over here, as you can see, because single thread is working over here. So all tasks share one track or one thread, and the CPU work blocks everything, right? But on the Rust over there, as you can see, there are multiple, not multiple basically, there are 4 threads, worker threads that are there, and the task has been divided into them. As you can see, the first worker get the 4 tasks, the second 3, third 3, and the fourth 3. So you see how this actual parallelism works in here, right? Because it is taking help of a CPU threads over here. So this is how Rust outshines Node.js when it comes to the CPU performance or any performance related stuff. Okay, see, Node.js is not bad. What I'm saying is there is a difference. There is a distinction between IO operations and CPU bound operation. That's what I discussed in the very first, right? So in IO operations, you really don't have to care about anything. Your main thread is free and you have to, the CPU sits idle basically, wait for the response, right? So Node.js is really well when it comes to doing something IO related, right? But when it comes to a CPU bound operations, I think the thread pool concept over here will outshine Node.js. So as you can see, I have multiple workers over here, and the task gets divided over here. Now when I take the runtime, let's see what happens. So you see, when I take the runtime, the Node.js is working over here on a single thread, while these 4 threads are working parallelly, as you can see on all of these. And when I do a tick again, as you can see, they all are working. And at that time, when we have everything over completed over here, Node.js also does the same thing, but it's in a single thread, right? And when I do a tick again, both of them completed. So this is how, as you can see, Node.js and Rust works. In Rust, we have multiple workers on the thread pools. You can call them thread as well. So there is no distinction on worker threads or threads. And the Node.js gives a kind of a single thread over here, that all the things that goes into the single thread, and it gets performed by this. If there is a CPU bound operation, that main thread that is working on these things will get bound. Okay. Now let's go on futures and polling. What are futures basically? So in Rust, when you deal with async await, the Rust kind of creates a state machine of that async await and continuously polling on them. So you must be wondering, hey, why Rust is polling continuously? Is there any infinite loop over there? Why it is behaving like any event loop or something like that it continuously checks on something, polls into something, are you ready? No, that doesn't happen. What happens is, whenever you assign something, whenever let's say you do an async await, it goes into the state, it converts it into a state machine, and it continuously polls on those futures by using OS level notifications. So whenever anything changes, the OS level notification generates, and Tokio just tracks them. So it is done by Tokio exceptionally well under the hood. So over here, as you can see, the async function compiles to a state machine, and each await point is a one state. Okay. So when we do an await, it's basically an state, and Tokio calls poll to advance it, to check it whether the things are ready or not. So let me just show this thing. So the state 0 is kind of let's say request.get thing we do, and we do request.get.await, right? So when I do an await over here, basically when I poll it, it checks, and OS started an HTTP request and nothing is returned yet. Alright, so when I poll again, it says that the future returns pending. Again, it's pending. And when I poll it again, as you can see, OS signals Tokio data is ready. See, there is a difference. It's not like any loop is running and it continuously polling into the future. Basically, the OS notifies the Tokio. OS signals the Tokio that, hey, the data is ready. You now try to schedule any worker that is available, any worker thread that is available on the pool, so that they can do the rest of the work. So one amazing thing over here is, when the poll is not ready, when you do a poll and the thing is not ready, the thread doesn't sit there. It's not sitting idle. It just go back on the thread pool and start working on something different. Okay, so now the response arrived. As you can see, OS signals Tokio and the thread is ready to just do some things. Again, there is a await over here. Why? Because when I pass the text, I have to await as well, right? So it's a different state machine over here. Again, it will wait for the OS level notification. So as you can see, when this thing is in await, and when parsing the text completes, the wakers again pokes Tokio. So this is how futures and polling works in Rust with the help of Tokio when we assign like multiple things and when worker threads are involved. Now let's see what work stealing is. So all these parts are there basically to show how Rust or how Tokio assigns threads to perform any things in Rust. Okay, so work stealing is, let's say all the workers are over here. Let's say there are 3 workers we have, and worker 3 is basically idle and worker 1 is kind of busy, has all the operations, right? Worker 2 is also busy. It has to do something like this, a DB query and like parsing a JSON, right? So what happens is the worker over here, the worker 3 will not set idle on the thread pool. What it does, it will basically steal half of its job, whoever has the maximum jobs over here. So when I simulate this thing, as you can see, the worker 3 has kind of stealed half of these things. So all of these workers are basically kind of working on something. They are not sitting idle. That is the true parallelism, right? So as you can see, worker 3 stole 2 tasks from worker 1. Now all 3 threads are running. A 0 code written for this, right? You are not writing anything for this. Tokio does it automatically. The Tokio is designed that way to use all the threads efficiently. Okay, now let's see Rust versus Node.js. It's like kind of this thing that we already discussed. It's just a summary over here. As you can see, if I have a 6 concurrent request, Tokio runs on a single thread. All of these requests are there. And while the Rust using Tokio, there are 3 threads assigned, 2 to each. So again, so if the parallelism is involved, obviously Rust will have the lesser time, right? Instead of Node.js. Amazing. Cool. So both process 6 IO tasks. Node.js interleaves on 1 thread, while Rust run truly in parallel across 3 threads. For IO, the difference is moderate, but the CPU heavy work, Rust parallel thread means 3 times more throughput than the Node.js singles thread when it comes to CPU bound work. Otherwise, when it's an IO related thing, Node.js perform really well on these things. So yeah, this is how async await, that seems very kind of a single word thing, that is how it works under the hood. I hope you understand this thing, how Node.js really works when it comes to an IO operation and how it lags behind when it comes to CPU bound operations, and how Rust with the help of a thread pool or an async runtime, let's say Tokio, and taking the help of all the cores of our CPU, it really outshines Node.js when it comes to CPU bound operations, and it can also perform well in the IO operations thing, right? So for the IO operations, if you are going, then choose Node.js, but you have to think like, does my work involve only IO operations? Then choosing Node.js is not a bad option. You can choose Rust as well because it can handle both of the things like IO operations and CPU bound operations exceptionally well. Alright, so that's it for the today's video. If you like this video, make sure you comment whatever you feels like, and if you have any questions, go on the comment section. I'll be happy to answer those. And like this video, share it with your friends, and subscribe to the channel. Bye bye. I'll see you in the next one.